The next unit we will work on is called hypothesis testing. This is related to the stuff we did with confidence intervals, but just approaches the problem from a slightly different perspective. So in chapters 10 and 11, we learn how to find confidence intervals for the population parameters in 5 different contexts. So the first thing we should do is name those contexts. So we had proportions. So P was one proportion. And then we also had P1 minus P2, or the difference in 2 proportions. And then we also had means. So mu1 population mean, mu d, which was the mean of paired differences, and then mu1 minus mu2, which is the difference in 2 population means. So next, we're going to conduct hypothesis tests for the same 5 population parameters. And this is related to the whole confidence interval things, because remember that in chapters 10 and 11, you could reject a value for a parameter as a value that was plausible if it fell outside of your confidence interval. And today, or like in these lessons, what we're going to have is something to the effect of, we think mu p thing is blah, and then we'll figure out how likely that actually is. So here we have an idea about that population parameter, like say, for example, mean body temperature is 98.6. And we're going to test to see if this is a plausible value using a thing called the hypothesis test. And in many ways, confidence intervals are better because having that range of values tells you, like, do you have a narrow idea of what that parameter is, or is your net kind of wide? But hypothesis testing is so common, and it's important you have some working familiarity with this topic. There were some statistical journals that back in the day required you to always do confidence intervals and never do hypothesis tests because you can make the same conclusions from confidence intervals. I still have to teach it to you. And here's the logic. The logic of statistical hypothesis testing is sort of similar to the presumed innocent until proven guilty principle of this US judicial system. This is actually why a lot of lawyers study logic, because the LSAT's a bunch of logic. In addition to other things, I'm sure, but I know that it does help. In hypothesis testing, we assume that the null hypothesis is a possible truth until the sample data conclusively demonstrate otherwise. So H0 is not guilty, which is our possible truth. So this is assumed true or plausible until proven otherwise. And HA would be guilty. So we say something like, okay, well, we found this person's DNA and their footprints and their fingerprints, and oh my gosh, that means that H0 is so unlikely that they must just be guilty. All right, here's an example of the kind of question you can answer with a hypothesis test. So suppose that your state legislature is considering lowering the blood alcohol content that constitutes drunk driving. And you, as, say, a representative, want to know if this proposal has popular support. For example, do more than half of the people support it? And you conduct a survey with 200 randomly selected people. Assume all of them answer. We're going to have perfect response rates. And 59% favor the proposal. Is this enough evidence to conclude that more than half of the people do so? And in this case, your null hypothesis, kind of like back in chapter 4 we had, was nothing going on. Well, that's that the proportion who favor the proposal is less than or equal to 50%. With symbols, that's P is less than or equal to 0.5. And HA is that the proportion who favor this is greater than 50%, or P is bigger than 0.5. And with these H naughts, the or equal to always goes with the null hypothesis. And the question that we want to answer is that, is this P hat of 0.59, is this big enough that we can say H naught is false? So we're going to learn the bits and the pieces, and then we'll put them together in some of the later lessons and actually do hypothesis tests. So first thing you have to know how to do is make the null hypothesis. We did this a little bit back in chapter 4 with chi-squared stuff. So the null hypothesis, which is represented by the symbol H with the subscript of 0, is a statement that there is nothing happening. The specific null hypothesis will vary from problem to problem, but it can be thought of as the status quo, this status quo, or no relationship or no difference. In most situations, the researcher hopes to disprove or reject the null hypothesis. The alternative hypothesis represented by the symbol HA is a statement that something is happening. In most situations, this is what the researcher hopes to prove. It may be a statement that the assumed status quo is false, or that there is a relationship, or that there is, say, a difference between two population means. So the first thing we'll do is we'll take a situation and try to write the null and alternative hypotheses from the statement. So suppose that a pharmaceutical company wants to be able to claim that for its newest medication, the percentage of patients who experience side effects is less than 20%. So the first thing you have to get is you got to get the right symbol. So this is going to be P because it's a proportion. So H naught, the thing that they want to disprove is that more than that many people, proportion, have side effects. So 20% or more suffer side effects. In symbols, I want you to do this both ways. It's P is bigger than or equal to 0.2. And HA, the thing they hope to be able to conclude is that fewer than 20% experience side effects. So P is less than 0.2. So the thing that they want to disprove is that their side effects proportion is bigger than this number. The thing they want to prove is that it's less than 0.2. This is an example of something called a one-sided hypothesis test. And say HT for hypothesis test. And that's because of the inequality going one way. We'll have this other stuff that is not equal to, and that's a two-sided test. A researcher wonders whether men and women have different average normal body temperatures. mu1, that's going to be the mean temperature for all men, and mu2 is the mean temperature for all women. So H naught, nothing going on, is that there's no difference in body temps. Well, in average body temps. So that would be mean 1 equals mean 2, or more commonly, mean 1 minus mean 2 is equal to 0. And HA is that there is a difference. Now, in body temp. Now, one thing to note is I didn't specify a direction. Like anyone who's ever had, held hands with a girl knows that girls have cold hands. Maybe girls' body temperatures are lower, but I didn't specify that in the problem. So there being a difference could mean that men's temperatures are lower, or it could mean that women's temperatures are lower. We don't know. So in that case, when no direction is specified, just mu1 does not equal mu2, or mu1 minus mu2 is not equal to 0. And this is an example of something called a two-sided test. And that is because either mu1 could be bigger than mu2, or mu1 could be less than mu2. Both of them are possible. And unless the problem specifies a direction, don't make up a direction. So we already did this, but a one-sided hypothesis test is one for which the HA specifies parameter values in a single direction. This is like example number 1. And a two-sided hypothesis test is one for which the HA specifies parameter values in both directions. This is like example number 2. So next, let's look at some statements and tell me whether they are examples of a null hypothesis, so nothing going on, or alternative hypothesis where something is happening. And then also state whether the test would be one-sided or two-sided. So the average weight of Canadian geese is the same as the average weight of Canadian warblers. So the same tells me that probably this is a nothing going on. So mean weight for geese equals mean weight for warblers. So this is a null hypothesis. And as this doesn't have a direction specified, this is going to be a two-sided hypothesis test. The proportion of books in the local public library that are novels is higher than the proportion of books in the university library. Well, this suggests that something's going on. Proportion in the public library that are novels is bigger than the proportion in the university libraries that are novels. This is an example of an alternative hypothesis. And because we specified that the proportion in the public library was higher than the proportion in the university library, this is a one-sided test. The average price of wool jackets in NYC is lower in the summer than the winter. Well, I think this once again is an HA. We have mean price in summer less than mean price in winter. All those jackets are on sale. So this is an alternative. And once again, it's one-sided. And finally, the proportion of students who receive A grades from Professor Harrington is the same, oh look at that, that's a hint, same or higher than the proportion of students who receive A grades from Professor Cantor. Because of the same, this is the null. Proportion for Professor Harrington is bigger than or equal to the proportion for Professor Cantor. So null hypothesis, one-sided. . Okay, so now that you can look at hypothesis statements, let's talk about the test statistics. So finding these test statistics is going to be kind of similar to finding your multipliers. So sort of like the multipliers thing. For CIs. So the test statistic is the summary that's used to tell you how far away your data is from the average. So is that 0.59 or 59% who support the making drunk driving laws more strict? How far away is that from 0.5? Like 1 standard deviation, 2 standard deviations? That's what this test statistic will tell us. And then the p-value, this is computed assuming that the null hypothesis is true, and then figuring out how likely is that test statistic. The test statistic is kind of just counting how far away from the mean are you. Are you 1 standard deviation above? What's the chances of that happening? Are you 2 standard deviations above? What's the chances of that happening? It's really just saying what's the chances that you'd be this big if that null were true. Okay, so here's an example. In a study, surgery patients either started taking painkillers before the surgery or did not do so until afterward. And among the pre-surgery painkiller group, only 20% still experienced pain 9.5 weeks after surgery. And in the other group, 60% still experienced pain after 9.5 weeks. So what your null hypothesis here would be that the proportion who received the person who received painkillers before surgery, the proportion who experienced pain is the same as the proportion who experienced pain after. That's what you're assuming is true. Nothing going on. They have the same incidence of pain. But then you found that one group has 20% still have pain, and the next group, 60% still have pain. That seems like a pretty big difference. And then the question is how likely is this difference? So how likely is this difference? I mean, it's possible that people in your painkillers after surgery, just a bunch of wimps who can't take pain. It's possible, but how likely is it? Well, you found that the p-value was, say, 1 in 500. Now, what that means is that a difference this large would only be seen in 1 in 500 samples. So a difference in proportions this large would only be seen in 1 in 500 samples. Or another way to say that, the probability of observing a difference this great is, 1 out of 500 is 0.002. That's quite unlikely. And so as this is unlikely, we can conclude our assumption that the proportion who experienced pain before, when taking drugs before, is equal to the proportion who experienced drugs after is false. So we said, if this happened, we observed this thing, and that's only observed in 1 in 500 times. That has a super, super low probability, therefore thing must be false. That's kind of a mathematical argument called contradiction. You say, I assume this is true, but then this unlikely thing is the consequence, therefore thing I assume must be false. Now, but there is often a threshold for what this P has to be sort of small enough to be probably not just due to chance. And that is the thing called the level of significance. So this is denoted by the Greek letter alpha, little fish letter. So this is the borderline for between when a p-value is small enough to choose the alternative hypothesis and when it's not small enough. When that p-value is less than or equal to alpha, we reject the null. So remember, a low p-value means there's a low probability you'd see that, which means your null probably was false. And when the p-value is larger than alpha, we cannot reject the null. It's common practice to call a result statistically significant when the p-value is less than or equal to 0.05. This is just a really common alpha value. So when the p-value is small enough, we reject the null hypothesis or accept the alternative. And small enough is defined as p-value less than or equal to your alpha, where alpha is a level of significance, which is usually 0.05. And when the p-value is not small enough, we conclude that we cannot reject the null hypothesis. Not small enough is defined as a p-value bigger than your alpha. Now, this does not mean that H0 is true. There are lots of reasons you could fail to reject H0. It could be because you have insufficient evidence. And what we're going to say in this case, something like this. We have insufficient evidence to reject H0. It may be true, it may not be true, you just don't know. It's kind of like what another student described this as is when this happens, this is like the reject research. You're hoping you were going to find a difference and you didn't, so that kind of paper gets tossed out the window. So state the conclusion that would be made in each of the following situations. If I had a level of significance 0.05 and a p-value of 0.1. So the question you ask yourself is your p-value, which is 0.10, less than your alpha value, which is 0.05? And the answer is no. So in this case, you fail to reject H0, or there's insufficient evidence to reject H0. If your level of significance is 0.5 and your p-value is 0.1, so is your p-value of 0.01, is that smaller than your alpha, which is 0.05? The answer is yes. Yay! You can reject H0 and you can accept HA. And this one, what if I lowered my level of significance to 0.1 and I had a p-value of 0.002? So is 0.002 my p-value? Is that less than my alpha, which is 0.01? Yes. Once again, you can reject H0 and accept HA. Now, in this hypothesis test, there are two different kinds of error you can make. And these names are actually named this way on purpose. What this does is it refers to which hypothesis is actually true. Where H0 is hypothesis 1 and HA is hypothesis number 2. So a type 1 error can occur when the null hypothesis is true. So H naught true, but you reject H naught. A type 2 error. So this is the kind of research where something is actually true and you conclude the opposite. So that's definitely happened. A type 2 error can occur when the alternative hypothesis is actually true, but you mistakenly conclude that the null cannot be rejected. So this is when you fail to reject H naught when you should. And type 2 error, this can be a lack of data, because there might be a difference, but you might need a bigger sample size to actually observe that difference. So here are some factors that can affect the probability of a type 2 error. So the sample size. So a bigger sample size implies the probability of a type 2 error goes down. The level of significance, well, a bigger alpha reduces the probability that you're going to make this error because it makes it easier to reject the null. Like if your alpha was 0.1, then you could have p-values that were, say, 0.07, and that would be okay. And the actual value of the population parameter. So the farther the true parameter is from the null value, the lower the chances you're going to have this error. So suppose a politician is trying to decide whether to vote for a new tax bill that calls for substantial reforms. A random sample of voters in his district leads him to believe that the alternative hypothesis, HA proportion is bigger than 0.5, is true, where P is the proportion of all voters in the district who support the bill. As a consequence, he decides to vote for the bill. So what would a type 1 error be in this situation, and what would be the consequences? So this would be to reject H naught when you should not. And accept HA. In this situation, this means P is less than or equal to 0.5, or less than half of his voters support this bill. And what that means, i.e., he just helped to pass an unpopular bill. What would a type 2 error be? Well, this would be when you fail to reject H naught, and when you should. So what you have here is you believe that the probability is less than or equal to 0.5 is possible. Like, you don't know for sure, but it's certainly possible when it's not. So when P is bigger than 0.5. And what this means here is that you did not vote for a bill that had popular support. And explain which error would be more serious. So would it be more serious to help pass something that's unpopular or to not pass something that's popular. And it probably depends on a bit of the situation, but at least your textbook says that this type 1 error is more serious. Voting for an unpopular bill can make people angry. And I would say also an unpopular bill that implements substantial reforms. Could have consequences. Angry town hall meetings. And the power of a hypothesis test is the probability that we decide in favor of the alternative given a specific truth about the population. When HA is actually true, power is the chances that we don't make a type 2 error. So a researcher is deciding whether to use a sample size of 100 or to increase the sample size to 200. Explain how this choice would affect the power. Well, you're less likely to make that type 2 error with a bigger sample. Less likely to make type 2 error with a big sample. So increasing sample size increases the power. In the next lesson, we'll actually do some hypothesis tests for proportions.